Hi, thank you for the introduction. Yes, today I'm going to talk to you about strong gravitational lenses, how to reconstruct them automatically with a recurrent inference machine. My presentation is going to be structured as follows. So I'm going to give you some background as to what is strong gravitational lensing. I'll give you an example of it. And I'll give you some application of these systems in cosmology and why we are a group of research interested in these objects. And then I'll give you my research goal. After that, I'll explain my methodology, what data we use, how we model the problem, and I'll give you some results. Okay, let's dive in. So gravitational lenses, as we know from Einstein general relativity theory, is that mass will curve space-time, and this curvature will make the light particle or the photons, which follow straight lines in space-time, they will make those paths curve around massive object, like we can see in this picture, the orange path that go from a distant source galaxy, follow curved path along around a massive object, which in this case we can see it's a galaxy cluster. And we curve around and we'll make images that we take here on Earth, either in space or on the ground. They will magnify images of very distant objects that would otherwise be super small and faint. And so they're natural telescope in that way. A good example of this is this one, where we can see in the middle a massive red elliptical galaxy in the middle. You can see here that will magnify a distant blue galaxy in the background in a shape reminiscent of a horseshoe, almost a full ring. These systems are super interesting to analyze. One of the reasons is that we can actually compute like the mass that's responsible for the deflection that we see. And this mass, we can compare it with the mass that we would compute for, say, the luminosity observed of the galaxy. And we can infer that there must be actually dark matter, that doesn't interact with light in any way. In this system in particular, there must be at least 60 to 80% of dark matter to account for the deflection that we observe. And this gives us application in cosmology, specifically when we have multiple of a population of these systems. So you can see here on the right, 6 gravitational lenses that were used to infer the expansion rate of the universe. I won't say much on this because there is an excellent presentation coming up by Ev on this specific topic. Another thing that these objects are really interesting in is, as we've said, they're natural telescope. They magnify faint and distant object, and we can then study, for example, the galaxy formation epoch of the universe, or when galaxy first started to come together, which is an epoch that's generally too far away in the sky for just our telescope to observe directly. So what are the challenges that are coming up in the next decade for analyzing population of gravitational lenses as well? There are large surveys that are coming up, like the Vera Rubin Observatory, which will take a full picture of the sky every 3 days. And we expect it to discover thousands of these systems. The problem is that analyzing a single system can take a few days, even months, and sometimes to fully reconstruct the mass distribution that was responsible for the deflection, and also the source brightness distribution. This is a major challenge since we need to analyze these large populations. So our goal is going to be to develop a fast and reliable reconstruction algorithm for these gravitational lenses. And a secondary goal that we set for ourselves was to be able to reconstruct a large range of mass distribution. So not just the simplistic one that we often use to reduce the complexity of the problem. So let us take a step back and think for ourselves, well, what is required to reconstruct these things? So first we need, we've got an observation here on the right. I present like a mock observation of a lens that I made from our data. And from this observation alone, we're trying to reconstruct two unknowns, so the source distribution undistorted, and the mass distribution, which is mostly dark matter. So we don't have a way to trace correctly the mass. We know correctly how to simulate. So in the forward direction, so if I gave you a source and mass density, you could easily reproduce this mock observation, but there doesn't seem to be a direct way to go from an observation back to the unknowns. In fact, there's an infinite amount of solution to this system, and so we need to go into a probabilistic framework where we need to set constraints on what source are possible and what mass distribution are possible. To do this, so for the sources in particular, it's quite easy. We can use the thousands of images of galaxies taken by Hubble telescope and other surveys over the years to construct a good data set of galaxy images. So we collected about 80,000 of those. For the mass distribution, it's a little bit more difficult to get those. We had to go into cosmological simulation and body simulation of the universe that recently were done by IllustrisTNG team to get realistic distribution of mass distribution, and then and these produce a large data set of lenses like I show here on the right. So those are going to be our constraints on what are possible for these things. And the way we're going to try to solve this system is, instead of trying to learn a function that's going to go from the observation and directly give us the source and mass distribution, we're going to learn an optimization algorithm where the model is going to be going to take steps in the candidate solution. So it's going to give us candidate solutions that are going to be better and better. After, say, 10 steps, we expect the model to have converged, and we can collect our prediction. This framework here is called a recurrent inference machine because it recurrently updates its own solution until it has converged. And a specific model we're going to use for this, so the G of phi I show here, is a U-net. So it has the particularity that so you can maybe recognize a U-net structure where at each level we're going to downsample or reduce the resolution of our features down to some bottleneck, and then reconstruct from those features images of the same resolution that we inputted before. So we input the source, the mass distribution that are our candidate solution at present time, and then this model will update it to make it better. And in the middle, we've got these memory units that serve as that are going to help us converge over time, that we put in each skip connection. That's the particularity of our architecture, where in a regular U-net you just have a skip connection all the way through. Here we put some memory units to help us converge and reconstruct at different level of resolution. So some prediction of this model so far. Here I show you an image very similar to the one before, but in each column I've appended the prediction of a model for you to compare. So for the source here and the mass distribution here on the right, there's a prediction, and the lenses here on the right, there's a prediction. So one particular thing that jumped to our eyes is that the overall the model at this point is able to reconstruct the overall shape of the lens very well. He's able to reconstruct very complex features of the source. But as we'd expected, the mass distribution is a lot harder. In fact, although the general shapes of the mass distribution can be reconstructed, there's a lot of very small features that are very hard to reconstruct still. But this is the progress. We're still working on improving those results, especially because we're interested in those smallest features a lot, because they inform us on dark matter and its dynamics, what it could be as a particle, and a lot of information like that. And in fact, those 5 examples that I show here may have been cherry-picked. So just to give you an overall sense of what the model does over like 1,000 lenses, here is a picture of of the similarity at each scale of reconstruction. So going from the large scale, so how much it can reconstruct the largest scale down to the smallest scale, and for the source, for the deflector itself, and for the lens. And as you can see, we're still having trouble down to the smallest scale. So yeah, for future work, for things we want to do with this project, we would really like to better understand what are the uncertainties inherent to the reconstruction process. We want to do more than just do the best prediction possible. We want to understand how certain we are that this is the correct prediction for each parameter predicted by our model. And we would like to compare our approach with traditional method, especially on very hard lenses. Like the first one I showed you, how well it stack up against traditional methods. So those are the future work. And in summary, the thing I showed you was that the recurrent inference machine can be extended to solve these kind of problem that I showed you, which are ill-posed nonlinear inverse problem with appropriate architectural change. So the architecture that I show you, we made specifically for this problem and a sufficient amount of data. So the data set that we constructed, which had hundreds of thousands of examples, through this it can learn good reconstruction. But to make the approach more robust, we'll need to we'll need to understand better the uncertainties and then apply it to real data to compare it against real methods. Thank you very much. This was my presentation.